So in class today, we talked about how energy is used in stoichiometry. And this is just covering page 6. And actually, before we even get to the stoichiometry part of it, you need to understand that even when you don't see a delta H value written off to the side of a chemical reaction, energy is involved in every reaction. It's either going in or coming out. And we can actually write those energy terms as part of the chemical reaction, just like all of the other chemicals that we've got. So let's go ahead and start off by filling in these first two spaces, thinking about what is going to be true about our reaction if our energy is a product or if it's a reactant. And when we're thinking about this, just visualize a super simple reaction. Reactants turning into products. If our energy or heat or anything, you might see this actually as the word or a number like 200 kilojoules, just written in a chemical reaction, just like any other substance. If that energy term is on the product side, just like all of our other products are the stuff coming out of our chemical reaction, then if energy is coming out of our chemical reaction, if we see that energy as a product, we know that that reaction is an exothermic reaction. And if I see that my energy is being put in on the reactant side, just like I just said, it's going into the reaction, just like all of these reactants going into the beaker, making the reaction happen. Well, if energy is going into the reaction, then that is endothermic. So we can see a reaction if it has those kilojoules, that energy term written in the reaction. Even if we don't see a positive or negative sign on it, we can tell whether it is endothermic or exothermic. So let's go ahead and get into some real stoichiometry with energy. And the good news is, like we were just talking about, because these energy terms can be written as part of a chemical reaction, we can use the balanced chemical reaction in order to write a ratio comparing the amounts of energy involved in or absorbed or released in a chemical reaction with the amount of substances that are being used to make that energy or to use that energy. So here, our first question asks us how much heat is released when 1 mole of glucose is reacting. And since we have a reaction here that's made all about 1 mole of glucose reacting, we can see that energy term on the other side. Then we can say and know that 1 mole of that glucose stuff would cause 2,560 kilojoules of energy to be released. This is just like a mole ratio. It's just instead of comparing moles of one substance to moles of the other, using this 1:6 mole ratio where both of these numbers represent moles. Now we're just doing a ratio between the moles of one substance and the energy that is involved in the reaction. So I think these are actually easier because every single thing we do this unit is all about energy. So every single problem that we look at is going to have something to do with the kilojoules. So you should always find those kilojoules first, and then figure out what other substance it's talking about. The next problem is talking about, okay, well, how much energy is released when 3 moles of oxygen react? Well, if I go and I find my oxygen here, then I can't do the same simple ratio that I did in the last one because my recipe, my reaction, is not designed around 3 moles of oxygen. So because my numbers I'm given aren't matching the numbers in my reaction, I'm actually going to have to do some calculations here. So as a reminder, when we do stoichiometry, that number from our problem is always the first number that we write down in our stoichiometry. And in all stoichiometry, anytime we're using a balanced chemical equation to convert from one thing to another, even if it's energy, every space in our stoichiometry setup needs to have a number, a unit, and a substance. So this is 3 moles of oxygen. That's our given. And then we're going to take this 6 to 2560 ratio and use that to fill in our next bracket. When I'm wondering what I should put, what part of that should go where, remember our diagonal rule. Any units that I start with in my given, I need to have those same units on the bottom of the next bracket. So if that's moles of O2 that I'm putting down there, then that means this 6 is also going to be coming down there with it. And if that 6 moles of O2 went on bottom, then the 2560 kilojoules is going to go on top. And this is the only exception to needing number, unit, and substances. There's not really a substance here when we have our energy. But if you want to help make sure that you don't forget that, if you want to make sure that you have 3 things in each space, then our substance, we could just say energy instead of a formula. So 2560 kJ energy. But we don't have to. The minimum is just number and kJ there. But every other number that doesn't have a kJ, kilojoules, on it is going to need number, unit, and substance. So if we multiply 3 times 2560 and divide by 6, then we get 1280. And because it was asking how much energy, and energy is being measured in kilojoules, then that is the units on my answer. So hopefully not too crazy. Now, we get to this next kind of section, and really, this is kind of a little side note that we've got going on here. We talked about how if energy goes into a reaction, and it's a reactant, then it's endothermic. If it's on the product side, then it is exothermic. And if you look at this original reaction here, since our energy is a product, that means that this is exothermic. Energy is being released. And then this quick little question down here says, well, what if the reaction is reversed? If instead of going from left to right and producing energy, releasing energy, we went from right to left, then the stuff on the right is now my reactants. I've just reversed the reaction. And if energy is a reactant, then this is now endothermic and energy is being absorbed. So even if this reaction doesn't have a double-sided arrow, we can reverse the reaction and do the kind of reverse of what we're seeing there. And that means that energy is going to be doing the opposite thing. The energy is going to be reversed as well. And so that maybe helps you understand why here it's starting to talk about how we're needing to use energy to produce this glucose that is now, it's on the reactant side. And if you look at that, it doesn't look like we should be producing glucose, but we can reverse this reaction. This reaction is actually cellular respiration, where we're using glucose to make energy for our cells. The reverse of that is actually the photosynthesis reaction. We take in energy along with CO2 and H2O. We can make that glucose and store that energy there. So we would need energy to produce the glucose. So even though it seems backwards from what the reaction is talking about, these reactions can be reversed, and we can basically do the reverse calculation. You just have to not care about the direction the arrow is pointing as much. Just kind of focus on the numbers you're given. Of course, the number from the problem is my given. And if it's talking about glucose, then we're going to be using this 1 and trying to find energy. We're going to be doing this 1 to 2,560 ratio. And I'm going to make sure that the 1 mole of glucose goes on bottom, and that 2560 kilojoules ends up on top. And now after I multiply those, this is going to give us a final answer of 30720. Although technically, since we only had 2 sig figs here, we want to round this to 2 sig figs. So that would be 31,000, closer to 31,000 than just 30,000, because that next number is a 7. And once again, this is energy, so that's going to be measured in kilojoules. So as we move down to these last couple of problems, this next set is kind of, once again, a little bit of a detour from doing calculations in stoichiometry. This is practice, looking at a few more reactions and trying to tell whether they're endo or exo, And I want to be able to have you tell me what the sign on the delta H is. If we were to write the delta H, the energy term, out separately, yes, it would be that number, but would it be a positive or negative sign once we write it separately? Once it's in a chemical reaction, no matter what side it's written on, it's always going to have a plus sign in front of it, because chemical reactions is all about what stuff we have. So here, after the reaction happens, I have CO2 and 393.5 kilojoules of energy. Here, before the reaction, I have calcium carbonate and 176 kilojoules of energy. So the chemical reaction will never have the negative sign in there, but I could ask you on a test or a quiz what would be the sign of the delta H for this specific reaction. And I would recommend that you first start by looking at where is the energy and thinking about, is this endo or exo? Where is the energy going? And here in the first one, since it's a product, it is exothermic. And then we need to remember and memorize basically that exothermic is always going to have a negative delta H. So we have to kind of take this as a two-step process in our brain, because it would be too easy to just think, oh, there's a plus sign there, that's positive, that's going to be endo. And it's easy to flip up. So you have to realize when it's part of a chemical reaction, what side it's on is what really matters there. In this next one, because the energy term is on the reactant side, it's going into our reaction. That makes this endothermic, and all endothermic reactions have a positive delta H. Okay, let's get back to a couple more stoichiometry problems to finish things out, and these are going to be a little bit different than the two we did earlier. Those two we did earlier were basically the same. We had some moles given to us, and it was asking us for energy. So, two, we're going to do as written. It is already different, and then I'm changing that question number 3 here so we can work a slightly different type of problem here as well, and I'll talk about that more when I'm ready to solve that problem. So in number 2, if you notice, it is asking us to calculate the amount of energy that is involved in a reaction, but this time the difference is my given value that I have to use to start my stoichiometry is in grams. So I can't just use the mole ratio, the mole to kilojoule ratio that I see here for my water and my energy. I'm going to need that eventually to get to energy, but because these numbers in our balanced chemical equation always represent moles, then that means that we are going to have to take one more step to get moles before we can actually use that ratio. And hopefully you are pretty familiar with how to get to moles from grams. It's the same way we always have. We'd have to look at the formula for water, H2O, and add up 2 H's and 1 O. And if you do that, hopefully you will agree that the molar mass of H2O is 18.015 grams per mole. And that means that if I have grams H2O on top, then that 18.015 grams H2O has to go on the bottom of the next bracket. The opposite side of our grams is always 1 mole of the same substance. And now we're in the same position we always have been. I've got moles of water here, and I want to get kilojoules. So I just need to go one more step using this red ratio we have there, making sure my moles of water are on the bottom, because that's what I had on top on the previous bracket. And then I can finish this out with that 572 kilojoules number. So now I just need to multiply all my numbers on top, divide by the numbers on bottom, and my final answer here is 238.134, but because I have 3 sig figs here, I can just stop after that first 3 sig figs. That 0.13 is not going to round my 8 up. And this is energy, so this is kilojoules yet again. But this next one is not going to have an answer in kilojoules. We've been solving for kilojoules a lot. Energy is one of the things we're curious about this unit, so a lot of times you are going to be asked to solve for energy. But what if we know the amount of energy we're using and we're trying to figure out how much stuff I can get or react with that much energy? So we're going to change this problem here. And like I have already done, I want you to cross out the words energy, involved, when, all the way through that 3.75 number. I don't want those there anymore. And then we're going to add this when 527 kilojoules of energy is used. So that turns this into a problem where it's asking us to calculate how many moles of aluminum oxide, that is, aluminum and oxygen, can be decomposed when a certain amount of energy is used. And just like always, the only number I've got in my problem, that 527 kilojoules, has to be my given. So this is going to look and feel a little bit different because kilojoules is our given. But as we read through the problem, of course, kilojoules is one of the things we care about, and aluminum oxide is the other. So I've got both of those things right here. So we're going to be using this 2 moles with this 3,352 kilojoules in order to get straight from kilojoules of one thing to moles of that aluminum oxide. And I probably don't need this line to be as long as it is because I can get to moles of aluminum oxide in one step. I've just got to put that number of kilojoules on bottom because kilojoules were on top before, and then the 2 moles of aluminum oxide. Made this line longer because I needed a longer one last time, but if this problem doesn't have grams, if the stoichiometry, this unit, doesn't mention grams, then it's probably just a quick little one-step problem. So if I do 527 times 2 and divided by 3,352, then I get 0.3144. And once again, I am keeping 3 sig figs because of the 3 sig figs in my given. So that last 4 there does not round up the 4 I've already got, and it'll just stay 0.314. And this time my units, not energy, not kilojoules, is going to be moles of that aluminum oxide stuff. So I hope this hasn't been too bad. It's just normal stoichiometry. It's just that instead of focusing on that mole ratio and all about moles in the balanced chemical equation, sometimes we'll see kilojoules in there. Now, I do want you to go ahead, if you haven't already, and work on worksheet 12B. This is all that same stoichiometry stuff we've been seeing. Some of it starts with moles, some of it starts with kilojoules, some of it asks for grams, some of it gives you grams, so be aware of that. Anytime you see grams, you need to grab a periodic table and add up the mass of that substance. And I have put the answers to that worksheet here on Canvas, or you can quickly jot these down to check your answers. And it's really important that you go ahead and change question number 4. We wrote and balanced all of these equations for you so you wouldn't have to worry about it. But unfortunately here, we incorrectly wrote the coefficients here when we were trying to help you with the balancing. So in question 4, these coefficients should be 4, 3, 2. And if you use these correct coefficients with the correctly balanced equation and these kilojoules over here, you should be able to get that same answer that I had just shown you on our Canvas page. 720 grams of iron is what we would expect there.